So we turn now to area inside a polar curve. And as far as calculus of polar curves goes, as opposed to the arc length problem, this is the very not boring part. This is the part that I think is actually much more interesting than than arc length. So the question is, and I've written it over here, is what is the area of the yellow region? We have some polar curve represented by this sort of purple blob, and we're trying to figure out what the area of the yellow region is. It's important to understand specifically what types of areas we can find in this we can find using this model. Just as, let me just draw this quickly, when we first started to do integration, we could find the area that was under a curve and between two vertical lines like this. When we're integrating in polar coordinates, what we're able to find instead is the area between two radial lines, which I've written as these two red dotted lines, where this one is going to be theta equals alpha, and this is theta equals beta. So that's the kind of shape that we can find the area of. It's not just an arbitrary shape. So just as how you had to get used to the idea that the limitations on finding area under a curve were that you could find the area between the x-axis, some curve above the x-axis, and two vertical lines on the left and right, this is now the shape you're looking for, is two radial lines at two different angles about the origin and the area that's inside some polar curve between those two radial lines. So in order to understand how we would do this, what you need to think about is something called a sector of a circle. So what I've drawn here, this is called a sector. This is this yellow region on the left that you see. It's called a sector. In other words, it's like a pizza slice of a circle. Now let's think about what the area of a sector is. So the area of a sector of angle theta is this. It's first of all going to be the area of the whole circle, which is pi r squared. That's the area of the full circle times whatever fraction of the full circle this angle is. Well, we know that the full circle is 2 pi, so this is going to be the full circle is 2 pi. So the fraction that theta makes of the full circle is just theta over 2 pi. Okay, so simplifying that, what we get is theta over 2 times r squared, or sometimes we write this as 1/2 r squared theta. So either of those gives the sector, or the area of a sector of a circle. Okay, so how are we going to use that fact to find the area of the yellow region on the right, the area inside a polar curve? The key here is to understand that what we want to do is take a little slice of this circle. This is always the theme in calculus, is we're taking a little slice of anything, and we're then going to expand on that. So what I'm doing here is I'm drawing a tiny little slice of this circle. And what I'm going to do is I'm going to say, let's just pick let's pick one angle within that slice. I'm just going to call this angle, let's just call that angle theta. I know that I've used theta for alpha and beta for the two boundaries on the bottom and top, but I'm going to say, let's just pick an angle theta. And let's call this little slice, the amount of the angle that we sweep through in order to get this green slice is called what we call any little bit of anything in calculus. What is that? D theta. You should have mastered this principle by now, that if I give you a quantity, if I say a little bit of Mars, if I say that I have something called Mars and I say I want a little bit of Mars, what do I call it in calculus? I call it d Mars. You put the d before it, that means the little tiny bit of it. So the total angle is going to be through which this green slice exists is called d theta, and we're going to use some value theta to calculate the full radius as if this were a circle. So even though, as you can see from the shape, the bowed shape of the purple curve, this is not the sector of a circle, I'm going to pretend that it is. In other words, I'm going to pretend that I had drawn a circle around that was based on how far that point is from the origin. Now I've blown this up a little bit so you can see it here. So I've blown up the image here. What was green striped region is now green highlighter. So what we have is we have this region, the green region exists through a little tiny angle that we're calling d theta. And as you can see, what I'm doing is, even though what I really want to do is find the area that's inside the purple curve, which I'll draw in a little thicker here, I'm taking into account a little bit of extra area. Why? Because I'm approximating the area inside the purple curve through the angle d theta as if it were really the sector of a circle, where I'm going to pick the radius of the circle by just picking one arbitrary point, one arbitrary angle around the origin, which I'm calling theta, like that. I'm going to plug that into the radius function. In other words, I calculate f of theta to get the radius, and then I pretend that what I'm really doing is calculating the sector of a circle of that radius. So let's see. So using this formula, we have the area of the green region is going to be equal to 1 half r squared times d theta. Except that we know that r is given by f of theta, so I can really write this as 1 half f of theta squared d theta, where f of theta is just the radius. Now, you should know where we're going with this. We have now the area, the approximate area of one tiny little slice of the region we're trying to find. Remember, what we're really trying to do is find the area of this whole region here between theta equals alpha and theta equals beta. So if we have the area of one slice, what do we do in calculus? We put an integral sign in front and we use it to add up all the slices. So the area of the yellow region, the area of, when I say the yellow region, I'm including, by the way, the part that's also shaded in green, that little green slice. So I have to, let's put in some more yellow there. The area of that region, just going back here, it's really this yellow region that I want to find, is equal to the integral from the low angle of alpha up to the high angle of beta times 1 half f of theta squared d theta, where, what is this? This is the area of one pizza slice. So I'm adding up all the pizza slices to get this particular portion of the region. And that's how area between curves, that's how area inside a polar curve works. We're going to put a box around this. This is the formula that you have to know.